today we have William Godsoe from Lincoln University in New Zealand as our speaker. He's a senior lecturer in the Department of Pest Management and Conservation. And his research is broadly linked to understanding biodiversity change and the mechanisms behind it and how species will respond to climate change and environmental change. And from what I read, he's working by combining different aspects of ecology, evolution, information, and game theory. So I think we will have a very interesting seminar trying to get to some of the mechanisms that sort of control biodiversity. And even his title is very interesting. So I'm really looking forward to hearing his talk. So the title is there more to life than information? And yeah, 104, I think we can start now. William, whenever you want, the floor is yours.
Thank you very much for having me. It's great to be able to give a talk. And I'll say that once I was invited to give a talk, I submitted an abstract based on a weird talk I'd given before. And I'm delighted that you guys didn't just throw it out and say I had to do something a little bit more normal. So I'll get started then. I'll be talking about if there's more to life than information. And I'll start just by sort of like the broad hand wavy part of why I think it's worthwhile for us to think about information broadly, which is that we're ecologists or biologists, population biologists, and we live in the world, but we live in a world where lots of people plan on using information to solve almost any problem that we have. And I have here a lovely screen cap. This is a screen cap of me trying to send a message to my mom, which I have to do through Facebook. And when I do that, the entire screen is absolutely chock full of different people trying to peddle different versions of information. My mom's name is in the bottom right-hand corner. There is an ad for Meta in the bottom right corner for their AI. Another ad for Meta AI in the upper right-hand corner over here, and then and then an ad for Gemini up here, and in addition, a help group for Claude over here. And so just everything we do in the world, I feel, is fundamentally saturated by this concept of information and digital things in the world. And I think that it's really one of the things that I think is most interesting about doing biology is that it often gives us a way to interrogate things that people find important and make new and interesting connections. And this focus on information is something that's popped up in ecology over and over again. I'll give one example of this. So this is Robert McCarthy, who's a very influential theoretical ecologist. This is, to me, like one of the very first papers on the concept of biodiversity. It's like a thing and an organizing principle in biology. And in that, he talks about different ways to measure biology. And he says, and one of the measures he proposes, he describes in the following way. We ask the question, how difficult would it be to predict correctly the species of the next individual collected? This is a problem which communication engineers have had to face because they're interested in the difficulty in correctly predicting the name of the next letter, which might appear in a message. And so a couple of things to say about that. So number one, like that is an intuitive way to think about biodiversity. I have a picture of mostly my kids here collecting an individual, and you might wonder what the identity of the next individual will be. But this description is really not that far from what we think about for chat models right now. And in fact, what Robert McCarthy is borrowing from is ideas from Claude Shannon, who developed information theory, which also pops up in the Claude AI ad in the middle of my screen up here. And so to me, there are these weird fundamental connections between this concept of information and what we think we're doing in biology, which I'm going to explore. I'm going to do that in this talk in 3 sections. So the first one is very much scene setting. And for that, what I'm going to do is I'm going to talk about why change in ecological communities can be interpreted as a form of information gain. Once I've done the scene setting for this, I'll then talk about how to measure gains in information in communities and nature. And then I'll do another talk based on a small published paper where I talk about how gaining information in the world can lead to unintended consequences. So we're going to start by doing the scene setting of why it is that the concept of information used in other fields can be related to what we do in ecology. To do this, I'm going to start with just a very simple illustrative example of what we might mean by information. And it's a talk, so we're going to be vague about it. I'm going to argue that we can think about information as a description of our ability to make guesses about the world. And I have here a example. I'm putting my picture right now next to this. This is a younger, more naive version of me when I first came to New Zealand in 2011, about the time of the 2011 Rugby World Cup. And this is a perfect problem for thinking about information. We can think about a guess that we have in the past, which is uninformed. So for example, if there is a rugby game and I want to know what the probability that team one will win is going to be. So that's a naive guess. And we can think about information as a quantitative measure of how new things change our guess. So we can have new information, which is the game is Canada versus the All Blacks. You guys probably don't think much about Canadian rugby, but I can assure you that they're not quite as good at it as the All Blacks would be, right? So that's a way to think about information. And we can just, for the sake of hand waving, highlight a pictorial version of this. So we think about bets that we could make in the past. So our old bet might be that there's some chance that team one will win and some chance that team two will win. And then we can update that bet when future information comes in that we think that one team is more likely to win than the other. And I'm doing this at an extremely high level, but one way that we can picture this view of information is to think about our old guess versus our new guess measured on a log scale. And I think I popped, oh yeah. And somewhere in here, I have a slide of just describing more precisely what this is. This is related to what we call a Kullback-Leibler divergence, which turns out to be a natural way to measure information. So this is a sketch that we've got so far describing describing our ability to make guesses. But in population biology, we can do something very similar where we think about the natural world. We can have a community of species that are out in nature. In that community of species, there might be things like maples and ferns. And we can think about how the abundances of different species change over time. And if you do that, you can start with a very similar sketch of the same idea. I start off with an old community where I have two species in equal relative abundances. I can update my community over time as one population increases in abundance relative to others. And we can think about how this updating then changes the effectiveness of the community. And one of the big things that we should expect to happen is that as one thing we can see that happens in this picture is that as we go through time, from the first generation to the second to the third, the community updates so that it has more individuals that belong to a species with a higher growth rate. And in this sketch, a consequence of that is that the total growth rate or productivity of the community increases over time. So as I've drawn the picture, it makes a very strong analogy between information gain and change in an ecological community. But I need to highlight one more thing, which is that organisms affect their environment, and this leads to limits in what actually happens in nature. And these limits are not very well represented by sort of the picture of information gain and our ability to guess. And we can think of this in terms of bets. It's fine to have a bet with 1-to-1 odds, 10-to-1 odds, 100-to-1 odds, 1,000-to-1 odds. All those things are very reasonable. But in an actual forest, if you increase the abundance of one species by 1,000 or 10,000, you run out of resources and your species will die. So when you put together this verbal argument, you can build up to something that's been in evolutionary theory for a long time, which is what's called Fisher's fundamental theorem. And one way to interpret this is that you've got an increase in the fitness of your community, and that can be set to be equal to the gain in information. So that's as you're switching species that are less successful for species that are more successful, minus these nebulous effects of the environment that have been in the literature for forever, but people have generally had a hard time to figure out how to measure. And here I've got the note, which I apologize I mentioned before, but I'll read it since it's here. For this version of Fisher's fundamental theorem that I'm talking about, we can think about information gain very formally as what's called symmetric Kullback-Leibler divergence. And I've deliberately not put the equation on, but we'll have time for questions afterwards, so we can talk about that if we need to. Okay. So what I've tried to highlight here is that the same basic picture can be used to describe change in a community and information gain using simple models. The real question then is how common are these effects in nature? And that's what I'm going to study in the second part of the talk, where I'm going to find examples of data sets where I can figure out how important is the information gain in natural communities. The first one I'm going to talk about is data that's readily available online, which is Gauss's original experiments on competition among different species of paramecia. And for this, I've got a picture of the paramecia on the left, and then on the right, I've got a screen cap of how these experiments were done. This is by Gauss, who was working in the 1930s in Moscow, and he'd set up very small, what we now call mesocosms, where you could put several different species of paramecium together, and then see the changes in abundances of the species over time to measure competition. When he did that, he got graphs that we don't always think that much about, but a lot of us have seen them. And I've put one up here, looking at a single mesocosm where you've got the abundance of different species of paramecia, which change over time. And this graph, as I've got it here, shows dramatic shifts in the relative abundances of the two species. P. aurelia, the green one, is initially roughly as common as P. caudatum, the second, the purple one. But by the end of the experiment, P. aurelia has essentially replaced P. caudatum. So that's a shift in relative abundances. You might as well think of it as like an updating of bets in favor of P. aurelia. And so it's information gain in that sense, but it's not clear how important that is to the total changes in the community. And one reason for that is something that Gauss notes at the time that people have talked about since, which is that in this experiment, and in almost any experiment that we can run, the environment will deteriorate as organisms grow. And I've pulled up, I think, a subsequent paper on this. So a lot of people have done follow-up experiments on density-dependent growth in paramecium. And what they say in this system is that over the course of experiments like this, the community seems to be accumulating toxins, which damage the growth rate of both species in the system. So you can think about information gain, but at the same time, you've got these other properties that are happening at the same time. And it's been challenging to measure this, but through my collaboration with colleagues, and in particular pestering Andrew Letton for several things, we're able to measure both of these things at the same time. And when you do that, this is what you get. You can measure information gain. It turns out that it has to be positive. You can only learn more over time, and you can measure it. But it turns out that information gain is absolutely tiny, is quite tiny. On this graph, you can see it as the small red line on the top over here. And it's completely overwhelmed by the total change in the environment. And so what you get is this huge drop here. This is indicating that the growth rate of the individuals in the community is slowing down over time, and it slows down enormously for the first part of the experiment and overwhelms the gain in information that you've got. When you're looking at that, one of the big things for me was just to be able to put numbers on this of how important information gain is. But I think there's actually some intuition we can get for this. So the measure of information gain works when you ignore limits in the environment. So it works really well when things are growing exponentially. But in a mesocosm, like in this experiment, growth very quickly deviates from exponential. And so at the very start, you can see both species growing up like this. That's close to exponential, but over time, the environment gets worse, and that drastically decreases the growth of both species. And so that, I think, is my synopsis for why we get this effect, where the total change in growth has this big dip, and that dip completely overwhelms the information gain that you get in the system. That, of course, is a very simplified system, and it's nice to have one that's easy to work with. We might wonder how common, how important information gain is in other systems. This is something that I'm working on right now. There are an enormous number of studies where people have measured, taken long-term observations of changes in biodiversity over time. And this is something that's still work in progress, but I'll just pull up a couple of thoughts that I've got from this. You can get a number of data sets, such as this one here, which is a long-term study on changes in abundances of rodents in the deserts of the southwestern United States. And in this study, you can pull out the same sort of things, a time series looking at shifts in abundances of different species in the ecological community. When you do this, you can again see that you get these enormous switches in relative abundances in the community. And so in some sense, then this looks like a form of information gain. You have species like this here. This is a pinion mouse, P. truei. And in some years, it is incredibly common, but then it drops in abundance and crashes to become much less common than other species over time in the data set. And so you've got a community, you have change, you can see that some species replace each other relatively quickly, but what you don't get is a simple relationship between the gain in information in the community and the growth rate of the community. And so in the simple version of Fisher's fundamental theorem, where everything depends on this information gain, what you should get is that as information is gained, the growth rate increases more. And instead, you get something that's in between noise, statistical artifacts, and the opposite pattern of that for this example data set, where the information gain happens in years where the growth rate decreases over time. This is a data set that's relatively simple, that's pretty messy to work with. And so I'm in the process of trying to reduce some of the errors and uncertainties in estimating the terms in the model. But I just want to highlight this, that it's worth thinking about how much information we gain in nature, and that may not be as important as we might think it should be. Okay. And we can put this back into the context of Fisher's fundamental theorem. And what we can say is that we've got that Fisher describes growth. Fisher describes an increase in per capita growth rate. He says that can depend on what I've described here as information gain. I suppose it might not hurt to mention that in Fisher's language in the 1930s, he talked about selection, but the terms are equivalent, minus the effect of the environment. So that's what Fisher describes in his model. But the information gain has been hard to measure directly. And yeah, and the relationship is not as clear as we would like it to be. Yeah. Another way that you can test the importance of information gain is just to see how the average per capita growth rate of the community is changing over time. If your communities are acquiring lots of information, you should expect their per capita growth rate to increase on average over time. And pulling up lots of observations from large, messy data sets that you can get from like the biodiversity database, what I've found so far is that the growth rate is neither increasing or decreasing in time. It's much closer to being fixed. And that's a lot of what I want to say for the first part of the talk, which is that from the first part of the talk, I've argued that ecology and information are deeply linked, and then in part two, I've talked about how we might be able to explore this link empirically, and what I've tried to show is that in actual organisms, information gain seems to be weak relative to limitations in the environment. Cool. that's the first part of the talk, and I realized I've been monologuing for a bit. I'm going to switch gears in a little bit. I just wanted to check to see if it was worth pausing for a question for questions at this point, or if I should move on to the next part of the talk.
We can certainly pause. If anyone has a question, also you can ask directly or put it in the chat and I can read it out.
A sip of water while I'm waiting.
I think people are quiet now.
Mhm.
Maybe let's continue and then
Okay,
we can have a conversation at the end of the talk.
good. Okay. So far, I've been talking about one body of work where we've talked about the idea of information and how it emerges naturally in ecology. This is something that we have a preprint that Andrew and I were talking about before, and you can pull this up. It's in review at Oikos, and I'm hoping it'll come up sometime in the near future. For the next part of the talk, I'm going to explore another idea around the concept of information. And I'm going to talk about, as we're doing management, what happens as we acquire more information about the environment. Um, this is a paper that's based on a collaboration that I have between myself and James Ross, who does pest management and work here in New Zealand, and Claire Postlethwaite, who's a mathematician, and I've sort of been sandwiched in between the two of them who work in very different ways. And the premise for this paper is that there are lots of problems in management where it's worth thinking about our ability to make guesses and how those guesses interact with other parts of an ecosystem. The talk starts off thinking about something that James has highlighted in his research, which is we're in a world where people talk about using AI to do management decisions in the natural world, and there's certainly lots of places where improvements have been made in AI. So in James's research, he talks about how it's getting better and better to identify pest species in New Zealand, such as possum, using machine learning or AI methods. And here I've got some screen caps that shows this. You have a thermal camera, and in a thermal camera, you can then identify organisms that we've got. And this talk is technically on a different topic from what we had before. But because it's a talk and the themes are pretty similar, I am going to assert that we can treat the accuracy of AI as a form of information gain. It meets the general definition of improving our ability to make guesses of something in the world, even though the exact statistic will be different in a lot of cases. Um, so now that we've talked about how we can improve our ability to make guesses about which species is there, we can ask when management tools can be improved by using AI, and when there'll be unintended consequences. And so for the next part, we'll just talk about working through some of the steps that go along with this. To do that, I'll create a model of how ecology and management tools based on AI might interact. And then I'll go through sort of a simple dynamical systems analysis of what happens. I'll talk about a one species system where you can get regime change, where the population ecology of a species can switch relatively quickly. And then I'll talk about a two species system where you could inadvertently damage a species of conservation concern. Okay, so to do this, I'm going to sketch out a relatively simple model. And for the first part of the model, this is just intended to be similar to anything else. So you have a model for the per capita growth rate of the abundance of different species, so like species Ni. And that per capita growth rate depends on the ecology of that species. And the way I've written this here is that the per capita growth rate is some function of other species that are out in the environment. And we can think of this as something like population, like logistic population growth for a single species model. So we have our basic ecological model, and then we're just going to add in a harvesting term describing management systems using AI. So we have we could have something like a trap which uses AI to decide whether to kill an individual that comes into the trap or not. And we can describe that trap with a couple of things. We have an ability of the AI to make a guess. And so that's the probability that a given individual will be killed based on the species that it's in. And then I've got this GI at N term here. And what that's describing is the details of how the trap works in nature. And the big take home that I have, and this is the great thing of working with James, who works on this topic all the time, is that the maintenance of the trap has a big effect on the outcomes for the population. And we can talk about systems where this happens in New Zealand. You can deploy traps. Traps will kill individuals of undesired species. And as the density of pest species increases, traps get used more often. This is something that you'll see if you go in the bush in New Zealand all the time, where you've got boring traps, where it's very common to see a trap with a stoat or a possum inside it. The trap, those are particularly simple traps, but the trap has sprung and it can't catch any other individuals in that environment until someone comes and resets it. So as the density of pest species increases, the number of traps that need to be maintained increases as well. And this can be in a number of forms. You can have to clean traps, you can have to reset them, there can be basic maintenance. And in this model, the way that we incorporate this effect is using a handling time term. So that it's like a type 2 functional response where the traps are very effective when the density of individuals is low, but as the density of individuals increases, the traps spend more time waiting for maintenance until eventually they can no longer trap any more individuals in the community. So we set up a model like this and then think about how these details interact with how AI can be used. So if you have a single species, and that single species, and then add traps that become increasingly effective at killing a species, you can get a regime shift, which is what I've shown on the left-hand side. So in the top panel, panel A, we've got a standard model of population ecology, where where your x-axis is the density of the species and the y-axis is the per capita growth rate. As the density of the species increases, the per capita growth rate declines until you get to a point where it's zero, which is essentially the carrying capacity. As you increase the ability of the trap to identify the species, the first thing that happens is that the carrying capacity of the species declines. So that so increasing the accuracy of the trap initially just means that the density of the species decreases. But as you increase the effectiveness of the traps further, you'll get to a situation where the traps are extremely effective when the species is rare. And that means that when the species is rare, it can be driven to extinction. So that's the arrow and the blue dot here. But when the species is common, the traps are not as effective. And so the population can persist in the environment. Then if you increase the effectiveness of the traps further, you can get to the point where the species is driven to extinction. And some of what I'm doing here, I don't mean as like it's shocking or bad or that big a deal, but just a reminder that in some parts of the world we talk about things like the accuracy of a model, but that accuracy can translate into weird ways when we try to apply it to an ecological system. And this just sketches that. Where things get more interesting is what happens when you have multiple species that are in the system. And so in the paper, we talk about one example of this. So we can have system in New Zealand. There are many places where there are birds of conservation concern. So that's panel B here. We've got a weka. And we want to manage to preserve the weka, while at the same time, there are pest species that we're trying to eliminate, such as rats. So we've got rats and we've got weka, and we can then move from dumb traps like panel C, which is like a very basic trap, to traps that use AI for identification. And this is a trap. that's in the catalog when we wrote the paper. It was supposed to come on the market in the near future that uses AI to identify species and to identify which the species associated with an individual and use that to decide whether to trap the individual or not. So in a system like this, you can think about the accuracy of the trap, both in terms of the number of rats that it identifies correctly. And for that, you want to be over here on the right-hand side of the screen, and also the number of weka that are identified incorrectly. So ideally, you'd like to identify all the weka correctly, which is the bottom. And it's really bad if you're doing a bad job of identifying weka, which puts you in the top right of the graph up here. So we've got these two things, and then we can put on the outcomes of interactions between rats and weka in the model. And this is sort of like the full phase diagram that you get when you do that. And for the parameter values that we have here, you can get a number of outcomes. In the lower left-hand corner, you get coexistence among the two species. So rats will persist and weka will persist. If your trap is too error prone, then weka can go extinct. If your traps are very good at your traps are very good at identifying rats, you have this relatively narrow zone here where you can drive rats to extinction, and you can then also have this zone C where both species go extinct at the same time. So a lot of what this graph is indicating is just that like the accuracy of your model can have weird effects on which species persist in the system, but you can also get interesting quirks like we found in other population ecology models. And you can look at the red dots I've got here. There are parts of parameter space where you can start off with a trapping regime, which is okay, and the species coexist. Then you can improve the ability of the trap to catch the rats. And as you further improve the ability of the traps to catch rats, you can move from the condition where the two species coexist into one where weka go extinct. And so by making your AI model better, you actually indirectly cause the extinction of the other species in the system. And in some ways, like if you've done dynamic modeling, things like this don't happen, can happen from time to time. I'll just highlight a little bit more intuition that you can have for why this sort of thing can happen. The first part is that the errors that you can make with a model change as the abundances of the species change in the community. So Hannah Burks, who's an illustrator, was working on a blog post based on this, and she did this lovely sketch of it. And it's just if you're in an environment where there are tons of rats, it's a pretty safe guess that the next thing you find is going to be a rat, and you can trap it with confidence. But in an environment where weka are overwhelmingly common, then the situation is murkier, and a small chance of producing of accidentally killing a weka could lead to undesired outcomes. Hannah then helped to do like sort of the full sketch of exactly what happens here. So you improve the accuracy of your model. That can lead to a decline in the population of rats. That in turn can lead to an increase in the population of weka. You can get more traps which are empty, and that in turn can result in more weka being trapped accidentally. And one of the things that's implicit in this model, but it also sort of powers this, is that rat populations can recover from extinction very quickly and much more quickly than weka populations can, based on the growth rate estimates that you can pull out. And so then this leads to a mechanism where you get unintended consequences, and the most extreme version of that is that you accidentally produce the extinction of a species of conservation concern. So just to summarize how to think about that, the big take home, I think, of this is just making better guesses is relatively easy. So like there's lots of opportunity for us to improve our ability to make guesses of some facets of ecology, but ecology is weird. And there are lots of ways that we can think of where you get indirect interactions among species that lead to unintended consequences. And it's just nice to be able to translate between our ability to make guesses and when these weird outcomes might occur. Okay. that's a lot of what I wanted to say for section 3. Our ability to make guesses in nature, I think, is probably going to improve a fair bit. There's a need to translate from this ability to make guesses into biology. And in the examples I've given here, I've tried to illustrate how adding a bit of biology can lead to weird outcomes. You can get regime shifts, and you can get indirect harm to non-target populations. And that's a lot of what I want to say for the talk. I'll just wrap up with a couple more things, and highlight that we live in a world where information is very common. I started doing a lot of this research just naturally assuming that information would be very common, very important in ecology, the way that it is in lots of other topics. And the more I do these papers, the more, the more I add some skepticism to that. From the two arguments that I've made here, from the couple of sections I've made here, I've tried to highlight that it's really easy to get information to emerge from ecological models when you have a simple model of ecology. And to picture when that model occurs, I've got one example of this here. I have on the left-hand side an example of a braided river in Arthur's Pass National Park in New Zealand. This is a highly disturbed environment where floods come all the time. And if you squint really hard, you can see individual plants in amongst the rocks over here. So this is an argument, say this is an environment where you've got individuals, they grow, they're spread apart fairly far apart. And so their opportunities to interact with each other in the environment have been limited. And these are exactly the conditions that emerge out of the model that lead to information being very tightly linked to ecology. But there's more to ecology and evolution, lots of other topics than just these circumstances. We have organisms that have lots of neighbors that interact with each other, that deplete resources, that pollinate or share mutualists. And all those are things that can complicate the relationship between information and ecology. And lots of weird things can happen when you in ecological systems where this is studied. And that's most of what I wanted to say. So that my argument after this is yes, there's a lot more to ecology than just information. And with that, I will thank some of the lovely people who have helped me to put together these two parts of the project. Thank you.
Thank you very much, William, for this thought-provoking